I really went to confer with Ms. Karen and see how she taught set 29, which is a really introductory level differential lesson. But knowing Ms. Karen, she probably went beyond the book. I don't know. So maybe this is review, maybe this is new. Have you ever heard of relative or percent error? No. Okay, then maybe this is okay. Cool. All right. So first, let's go with the lesson is differentials, and let's talk vocabulary. Actually, if I just said what's a differential, what would you say? dy. That's a differential. What else? Yeah. dt. Anything. Okay. dd. Microscopic change in a variable. Right. Now, what is a derivative?
Rate of change.
A rate of change. Rate of change at a point or over an interval? At instantaneous, yeah. Okay, instantaneous rate of change. How, now that, if you think of that again, just to go back and blow your mind again, how do you get change between a point and itself? Yeah, you really can't, but you can say 2 points, change between 2 points and then get the points closer and closer together, and it approaches pointing at change at a point, yeah? So the definitions of the derivative all do this by saying, finding the average rate of change, which maybe looks something like this, the change in y over the change in x, and then getting the points close together using a limit. They all do this in some fashion, all three definitions. I'm just giving the first definition of the derivative, but they all have rate of change of 2 points approaching rate of change at up. Now, frequently we estimate instantaneous rate of change with average rate of change, especially when we don't have an equation to actually take a derivative on. All we have is actual points in time that they took measurements at. So for example, if we had this table of values, then I could estimate f prime at 3 by saying that's approximately the average rate of change close to 3. What points do you want to take? 2 and 4. Okay, if you use 2 and 4, that is mathematically sound, and if you do that, what definition are you using? The on each side definition, or the nope, not all. Symmetric definition. If you use 2 and 4, then you're going on both sides, and that's fine. And isn't that something like -4? Could you also use 3 and 4? Yeah, that's fine. If you do that, then your average rate of change might be less than this. -10. Could you use 2 and 3? Sure, or 2 and 3, you get the point. It's not very simple. Okay. All right, now then, the idea is average rate of change can be approximated by the derivative. We do that when we use a tangent line, and the derivative can be approximated by average rate of change. It goes both ways. We sometimes know the derivative, like a tangent line, and we can use it to estimate the average change, or sometimes it goes the other way and we estimate the derivative like we just did. All right, when you use differentials, you're using the derivative to estimate change. Goes a little like this. As I just said here, on small intervals, really this only applies to if you make a kind of small window around the derivative and the actual change, then you're close. But surely the further you increase the window, the bigger the gap between the expected rate of change and the actual amount of change, right? So for small windows, the average rate of change or secant slope is like the tangent slope. Now, the true change in the function is delta y, how much we actually changed by. Shall I draw a picture in the notes here? Yeah, would you draw a curve? Put a point of tangency and draw a tangent line, right? Okay. Now, actually, can I undo that? I know love students love that, right? So imagine a curve is changing up to that point, right? All right. So if I took at that point a snapshot and said, all right, based on the way it's sloping at that point, I could say in the future I would expect it to change like this. And so if I wanted to try and estimate how much y would change by, because this is a tangent line based on a rate of change way over here, this is really going to be more like an expected change in y, dy, based on the calculus. Now, the true change might be that the curve says, faked you out, I actually turned up. Now, this, from here to here, that's how much y actually changed by, a true change in y. Now, if I kept that closer, those two would have been a heck of a lot closer and less error, but I never know how the curve is going to curve away. The idea then is we're going to use dy, or how it's changing at an instant, to try and anticipate how much it's going to change over a time frame. Now, when you do that, start with this idea, and if I try and isolate delta y, then wouldn't that mean delta y is the derivative times an amount of change in x? And that then is the big idea of the day. Delta y is approximately dy, and dy is the rate of change at a point times an amount of change that I'm going to go over here. I would take into account how fast it's sloping and how much I'm changing x by, and that'll give me an estimate about how much I would expect y to change by. Now that's the idea of differentials. And let's see how we'll do more of a real life problem or two first and see how it goes, all right? So check this out. The radius of a spherical balloon is 3 inches. I don't know if you need a picture, but it's fun to draw. Cool. Use differentials to estimate how the surface area will change if the radius goes by a 1/4 inch. Now, it says use differentials to estimate how it will change, not find the change. So I could take the surface area at 3 and the surface area at 3 1/4, subtract, and that's true change, okay? But it's often the case that calculus is quicker, especially because calculus involves taking derivatives, less power. And so differentials are often easier to find than true change. Sometimes true change can even be found, right? So I know you'd like to just say, why don't we just find the two surface areas and subtract? But we're trying to learn on an easy one here. So this is the idea. You want to find true change in surface area. And you're going to estimate that with differentials, which is a microscopic kind of or expected amount of change in surface area. That's the starting point. Now, when we find how much surface area will change, we first need to find the rate at which the surface area is changing. Now that's a ratio of surface area change to radius change. And then we need to multiply that by how much the radius will change by. So by d r. I'll say that again. The surface area prime is like a rate at which, a ratio of how surface area changes with radius changes. So if I take this surface area change to radius change rate, multiply by some amount of radius change, I'll get surface area change. You with me? Are you with me? Okay. And we know surface area. Do we know surface area is 4 pi r squared? Okay. So what is surface area prime? 8 pi r. And at what r will we find the rate of change? The rate is 3. And the dr. How much are we going to grow the radius by? 1/4 inch. Is it plus 1/4 or minus 1/4? Plus 1/4, because it is growing, the sign does matter. All right then, I would expect that based on how it was changing at that instant, As the radius grows by a quarter inch, I would expect the surface area to change by approximately 6 pi, what units? Inches squared, because it's change in surface area. You follow? Okay. Let's look at this a little different way, maybe a little closer to what you might do in science, but maybe not. Okay. If I held up a ball and said, guess how big the surface area is, or the volume or the diameter of this ball, okay? And you all took a guess. If the average of all the guesses was 12 centimeters, but based on the whole range of all the different measurements, seems like you guys could be off by as much as a half a centimeter on either side. Now, based on there being error in the radius, or the diameter, if I then use that estimated diameter to try and figure out the volume, then I'd also get volume error as well, right? And when you get error based on a previous error, that's propagated error, and we're trying to estimate the propagated error. So let's start here. The starting point is, what are you trying to find or estimate? Use differentials to estimate the possible error that would result in using the radius to calculate the volume. So we're trying to figure out or estimate the error in the volume. Now the true error in the volume is delta V, how much it could be changed by or off by. We're going to estimate that by the idea is differentials. So the differential for delta V is dV. dV, or how much volume will change by, is the rate at which volume changes with respect to R times an amount of R change. So times dr. That, just so we're clear, that better be on every problem. That is the idea. And if you don't have that, if you just rush ahead saying, okay, the derivative is this and the numbers are that, then that's like a paper without a thesis. That's just random facts thrown around. That is the idea. That's the governing idea of the problem. It better be there. Understood? Okay, so what is V prime? If V is 4/3 pi r cubed, then V is 4 pi r squared. At what R will we evaluate that? R equals, not 12. The diameter is 12. The radius is 6. Oh, this says radius is 12? Oh, sorry. I thought you couldn't read, but it turns out you can. You can both read. But yours says radius is 12? Okay. All right, and what about the dr? 0.5. Positive or negative? Both, yeah. I don't know if it could be off by as much as 0.5 on either side. So that's then 4 times pi times 144 times 0.5 with a plus or minus out front. So half of 4 is 2 times 144 is 288 pi plus or minus in the units. Centimeters cubed. By the radius being off by a half of a centimeter, the volume could be off by as much as 288 pi cubic centimeters. All right, are we good so far? Yes?
So, the thing you highlighted, do we have to have a squiggly equal sign between
Yes.
UV and...
Oh, here? No, these are equal. Yeah, I mean, this is the way that in my simplistic mind thinks about it is, this is just a mixture of Newton notation and Leibniz notation. I mean, this is just the derivative two ways. If I move this over, then it's still hard equal. Yeah, it's the delta that's just a... Thank you for asking. Okay, now, all right, so we estimated a sphere, and we got 288 pi cubic centimeters. Now, the logical question, at least if you're a logical person, would be, is that a lot? Well, it kind of depends. I mean, if you were measuring a P, and you were off 288 pi cubic centimeters, is that a lot of air? Yeah, but if you're measuring the sun, and you were off 288 pi cubic centimeters, is that a lot of air? That's nothing, okay? So the answer to the question, is that a lot of air, is it's relative. It relates to what you're measuring. I mean, the number is kind of needs to be related to what you're trying to measure to say, is that a lot or not? So the idea of relative error is to take that estimated error and relate it to what you actually measured to begin with. And that could either be in a decimal form, relative error, or percent form, where you just take the relative error and make it a percent. If we wanted to, for the previous question then, if I wanted the relative error, then I would take dV to V. Now the absolute value negates the plus or minus, so don't sweat that anymore. What was dV for us? In the previous problem, 288 pi, is that right? 288 pi. The volume is the volume of the sphere at its original point, so 4/3 pi r cubed at an r of 12, yeah? You down? Okay, so that's 288 pi times 4/3 pi, I guess the pi's will divide away, 12, 12, and 12. Let's do a little cleanup. Wouldn't you say that 12 and 12 is 144 and goes into 288 two times, eh? I feel like I'm kind of making a mess of this. Isn't that 6 over 48? Did I make a mistake? Are we good? I'm kind of all over the place canceling, but 1/8 or 0.125 is the relative error. And then the percent error then is, obviously, 12.5%. Now, depending on the standards of your industry, you'd say, holy crap, that's a lot of error. Well, that's pretty good. Okay? For the hard sciences, I would expect that's probably pretty terrible. But for social sciences, you think, yeah, sure, there's something. So, pseudoscience, you might say. Don't tell me this Western Union. Is this social science? Yeah, don't tell me this one. Okay. Anyway, use estimated change by differentials to estimate a new value. Now here, this is going to look a little like a tangent line. There's probably 70% overlap with a tangent line. If I use differentials to estimate the square root of 47, I could say this is close. This is, actually, let's go here. This is square root of 49 plus some change. I could think of it as starting as a good point nearby as square root of 49 is the closest near good root. Now I could approximate that with 7 plus, instead of delta y, I could approximate it with dy. All right? 7 plus dy. Well, how would you find dy? Let's let y equal f of x equal what function? Square root function. Okay, so I ask you again, how would you find dy? The derivative, so let's just call it f prime at what point? At 7 or 49? Which is the x? You put 49 into the square root and 7 comes out, or do you put 7 into the square root and 49? So I ask you again, what's the x? 49. Okay. And what is the dx? Actually, let's write the formula first and then I'll do the dx, sorry. Okay, so 7 plus, what is the derivative? 1 over 2 square roots of x at 49. And what is the dx? It's not on the back of the page, it's up here. What's the dx? From where you start to where you're trying to get to. Almost there. It's not 2 though. It's not root 2. Okay, where are you going from? Where are you starting? 49. And where are you going to? And how far is that? Try again. -2. It's 2 down. You're changing x by -2. Okay, this comes from 49 to 47 is -2. Where you start, or the good point, to where you're trying to end, or where you're trying to estimate, and that's -2. Now that makes sense, because shouldn't we be, if we're trying to root 47, aren't we going to be a little less than 7? Yeah. All right. So here we go. 7 plus, what's the rate of change at 49? 1/14. You could look at that as y changes 1 for every x change of 14 units. But I'm only changing x by 2 units, so y will only change by -1/7 unit, and so our estimate is 6 6/7. Now that is exactly what you'll get with the tangent line. It's just a little different way of thinking about it, but like I said, the calculus is a lot of overlap. You tried some. This is, I used to just say, all right, do you get it? And I got a lot of it. Made sense when you were explaining it, but now I don't understand. So now you need to try. Feel free to work with your mathematics. I imagine you can use your calculator pretty good. No question. No, like mathematics. Say again? Oh. Does it matter?
Yeah.
Just a little. Just to the G and the S is a miles per hour. Because we'd have to change them.
So I don't think the units will matter, but let me explain why. So do you agree with my big idea here? And that's d prime times d s, right? D is a function of s, yeah? Okay, so let's talk units here. What are the units on d prime? That's d ds now. So change in d. What's d? Feet, and what's s? Miles per hour. And what's ds? Or what's ds? Miles per hour. So what are the? You're good. The units are non-issue. Yes.
So for this one, when we get to the d prime of s, do we evaluate at 35 or 36?
No, the original. Always the original. But just like your tangent line would always be drawn at the starting point and go to the new point, the derivative is always at the original. Let me catch up to you and see if I.
It's always the original.
Yes.
So you're trying to s from that.
So did you get? Sorry, catch up to 1.1
Gary,
plus
can you change your rating?
8
If you're going 1
s. That's an s.
it's not. That's the total stop.
Times 35. Did you get 38.9? No. Ah, shoot. What did I do wrong? You disagree with my derivative? You got the same derivative? Oh, my bad. Sorry, I moved the decimal point one. Sorry. Okay, let me try this again. 0.1. Did you get 4.88?
Yes.
Okay, cool. 4.88. So by going 1 mile an hour faster, you just increased your stopping distance by 5 feet almost. Okay. Did you give you another minute to work on this one?
Yeah.
Okay. What's the surface area of a cube? Or whatever, you can call it S. I don't call it, there's no known formula. You can call it S if you want. I called it X. Did you get an approximate area change or error of 45 square centimeters? Obviously not done, you still have more to do. That's not fitting. got there? Oh, wait, no, I'm sorry. Oh, wait, no. 1 6 times 7 is 45, so 1 over 7.5. So what do you get there?
So how do you get 1/7.5?
I took 6 times 7.5 and hacked away 45. This is down here is 6 times 7.5 times 7.5, yeah. 6 and 7.5 is 45. Yeah, I know, so that's why I still have a 7.5. I used 1 to hack away with the 45. So what did you get there? 100 divided by 7.5 is 13.3 repeating percent. Error. Okay. You get the gist? Ish. Okay, questions on 98? The what? The replacement?
Yeah, I just don't.
There's one more part? Oh, so that's just reviewing, did you learn anything? Did you learn anything? No? Who said no? Get out. All right, 98, go. 13, replacement. 3. Does anybody?
Just 3.
3A. Does anybody, do you band people need this? Do you have this?
I'm not ready, sorry.
For the homework? Do you have the homework?
Gave it to us.
I did? Hey, there, I'm gonna, because there's so many of you, band people. Yeah, I'm good. Sorry. There, here's what we did yesterday, band people, Saeed. Alright, I would hand it out, but then I don't have any questions. Alright, 13 is 13 out of the book. Yes, okay, here we go. Darn it! Should we keep this till tomorrow or can we turn it in? Keep it? Really? Alright, keep it till tomorrow. Alright.
Do you think we're gonna watch the show?